Hi everybody. We're going to start our third video, which is with continuing stoichiometry. So let's just get started here. First of all, you're probably wondering what in the world stoichiometry really means. So far we've looked at molar mass and we've also looked at empirical formulas. But really what we're trying to do is look at the study of quantitative relationships between reactants and products in a chemical reaction. So what this means is the first thing you always need to start with is a balanced reaction. And we have been doing these in the past, so hopefully this skill set will still stay with you because it just doesn't seem to go away. So what we're doing is we're going to balance a chemical reaction and then we're going to find the amounts of other reactants or products. So to do this, first of all, you need to remember or know how to complete and balance reactions, very important. If you do not, please make sure that you're going back a little bit into my previous videos or reviewing some of the stuff that we've been doing to make sure you understand this. You need to be able to convert between moles, mass, the number of particles. Remember, we needed the 6.02 times 10 to the 23rd. And we're going to be introducing one other thing, which is called the volume at STP. We'll talk about this a little bit later, but what that means is standard temperature and pressure. Okay, so that's going to, if you see this word STP, that is a very good indicator that you're going to be dealing with gases, and you have your own little set of criteria that goes along with that, and we'll explain that later. So as a quick review, a mole is 6.022 times 10 to the 23rd of anything. That's Avogadro's number. Usually we use this though in chemistry. So if we had 1 mole of any substance, it would equal 6.022 times 10 to the 23rd. And remember, you'll see the following things like atoms, molecules, form units, bananas, whatever. Okay, but that's just what that means. It's 6.022 times 10 to the 23rd. However, whenever we're looking at molar mass, now we're looking at how many grams are in 1 mole of a substance. So if we look at 1 mole of carbon, we need our periodic table. We look at the bottom and we notice it's about 12 grams. If we look at 1 mole of CH4, which is methane, we would need to calculate 1 carbon, and we would also need to calculate 4 hydrogens. After we add both of those up, we should come up with 16 grams of methane. So hopefully that is a good review of just molar mass. Okay, so let's just do this one more time here. We're going to start with our given, okay? Always start with what they give you. They give us 43.2 grams. This helps us to set up our train tracks, if you want to call them, so that you know how things are going to cancel out. So it wants us to convert 43.2 grams of sodium into moles of sodium. Well, I'm going to put my grams down here. And if I ever have grams per mole as our units, that's a very good indicator that I need to go and consult my periodic table. Okay, once you do that, you're going to put down what you have here for your sodium into your moles. And looking over at the periodic table, we notice that it's approximately 23 grams for every mole. Okay, so now you just simply do the math. This is in the numerator, this is in the denominator. You just take your 43.2 and you divide it by 23, which I'm going to do here. And we get 1.87. Okay, so it's not too hard, 1.87 moles. These are going to cancel away. Okay, let's look at another problem. Once we, well, let me just go over this mole map first. So that was just wrapping up something that should be pretty easy. We've done these before, but I have this under your modules and you can look this up. This is just a mole map and it'll help you keep track of things. To read this, you're going to use these volumes of a gas whenever we, if you see, like I said, the word STP in your problem, then you're going to have to go this route. You're going to have to start here and then go wherever it wants you to go from there, okay? Generally speaking, though, if you're not dealing with STP, then you're dealing with probably some sort of mass of a chemical. If you do, then you start with the mass of a chemical. So let's just say this was 23.4 grams of sodium, okay? And let's say we were given a chemical reaction and we needed to find out in that same reaction hydroxide. Well, the first thing we would do is we would take the mass of chemical 1, which I just said was sodium, okay? And then we would try to get the moles of that by using the grams per mole ratio. After that, you would do the mole to mole ratio of your balanced chemical equation. I'll talk about that in a couple minutes. And then you need to find the moles of chemical 2, which would be hydroxide in this example. And then finally, you would need your molar mass on the periodic table to find out the final mass of hydroxide. So this is how we can scooch from one chemical or compound in our periodic table to try to find out something else and how much it reacted in your on another part. So if you need to go further on down, we talked about these at the beginning of the year, then you would need your number of particles. Now here's just a review of some of the information to help you with this. Again, Avogadro's number, 6.022 times 10 to the 23rd particles per mole. That's what you're going to need down here. See, you need that Avogadro's number if you're going to go from here to here or even from here to here. Okay, and when you're going towards the mole, if you're going towards the mole, you're going to divide. When you're going away from the mole, you're going to multiply. Okay, so that's just something to kind of memorize. If you are up here using the volume of a gas, you're going to use this right here. It's called molar volume, and that's 22.4 liters per mole, or you also see it 22.4 decimeters cubed per mole. Okay, decimeters cubed and liter are synonymous with one another. And again, there's that key word STP. If you see STP, you're going this route, and you need 22.4 liters per mole to help you get to the moles of this. And we'll do a problem like this later on, so don't worry. The mole to mole ratio, if you're wondering what that means, you have to look at the coefficients of your chemical equation, and that'll tell us how many moles reacted of one substance versus how many reacted into another substance. So let's put this in practice. You might want to keep this mole map in handy if you want to go to your modules and print it out, or just take some notes on it and keep it handy for yourself in class. Okay, so this is what I meant by these coefficients, moles and reactions. Note that all of those conversions involve moles. This is just another way to tie into reactions. So if we had 1 mole, this is just a 1 of propane, reacting with 5 moles of oxygen, and it'll make 3 moles of carbon dioxide and 4 of water. So these coefficients are the same things as the number of moles reacting. Okay, so this is going to lead us to the idea of mole ratio, which is a ratio between two chemicals in a balanced chemical reaction. So if I were to look at oxygen versus carbon dioxide, 5 moles react to every 3 moles of carbon dioxide. This is going to come in handy in a couple minutes. Okay, so let's go ahead and do this problem. We're going to start here with this balanced chemical equation. It's step 1. Make sure that you are dealing with a balanced chemical equation. And we're going to give our given, which is 5.2 moles of propane. That's where we're going to start. So we have 5.2 moles of propane, C3H8. And it wants to know how many moles of water could be produced. So this is my ending point. Okay, so we're going to set up our train tracks. Now you might be wondering, well, how do I scooch over automatically from moles of propane over to water? You have to use your mole to mole ratio. Okay, you have to bring that into play here. So for every, this is 1 mole, this is understood to be a 1 right here. For every 1 mole, and I put this at the bottom so that this will cancel with this, C3H8, okay? There are 4 moles of water that react. Okay, that is what we mean by our mole to mole ratio. It's an intermediate step that you need before scooching over to the next part, okay? Now this only asks us for moles of water, so I'm going to stop here. So I simply multiply this by this, and you end up with approximately 20. I could do the math to make sure exact amount, but 20.8. I guess that was pretty easy in your head. Okay, 20.8 moles of water. All right, let's try another one. How many moles of carbon dioxide, okay, this is where we want to stop, would be produced by burning 5.47 moles of propane? Okay, well, let's start with our given always. C3H8. I want my, automatically, these moles of C3H8 to cancel out. So I'm going to put that right down here right away. Okay, there's only 1 mole, so that's just, I'm going to put 1 here. It's asking me for carbon dioxide. I want to do my mole to mole ratio. Well, there are 3 moles of carbon dioxide. Okay, so there's really, that's all there is to this. And then we just multiply that across. Okay, approximately 16, but we'll find out the exact answer here. 5.47 times 3. 16.41. Okay, and these are going to cancel out. All right. We can keep on doing this. Now, how many moles of oxygen? Okay, this is our endpoint. Will be needed to burn 4.8 moles of propane. So we're just going to start here with our given. Okay, I'm going to put this propane down here at the bottom because I want those to cancel out. I want moles of oxygen up on the top. We know that there are 5 moles of oxygen that are produced with every 1 mole of propane. Okay, so now we just simply do that math. We get 24. So hopefully you're seeing that these aren't too bad and that you're not going to get all scared of these. Okay. So this last part that I want to talk about briefly is if the pressure and temperature are constant, the ratio of moles in a balanced equation is the ratio of liters in an all-gas reaction. So I talked about this STP before. That just means standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. Okay, so these are constant. These are standard, 0 degrees Celsius, 1 atmosphere. If you have these standard conditions, then this is what you're going to be using. 1 mole of gas is equal to 22.4 liters. So let's take a look what that looks like. If we have 17 grams of magnesium, okay, start with a balanced equation first of all. See, now we have to go and balance this. We have 2 there, and we have 2 there. Okay, so we're good now. So we have 17 grams of magnesium, okay, and we want to know how many liters of hydrogen form at STP. Okay, well, let's go and start first of all and get these grams to cancel out. So we look over, I'm going to get out my little chart here. Okay. Okay, so I looked it up and it is 24.31 grams of magnesium for every mole. Okay, so those grams are going to cancel out. Make sure you put down these elements as you're going along, or you're going to get confused. Okay, now I need to go from magnesium, scooch over to hydrogen. So what do? I use that mole to mole ratio by looking back at my balanced chemical equation. I want my moles of magnesium to cancel out. Okay, now how many reacted? 1. So I put 1 mole magnesium here. And how many of the hydrogens reacted? 1. So I have 1 mole of hydrogen gas to every 1 mole of magnesium. Now those are going to cancel out. Okay, it's asking me for the liters. Okay, so instead of going to grams, because I don't need grams, I'm dealing with a gas right now, we know that we instead have to use 22.4 liters of hydrogen gas for every mole. That was the conversion factor of hydrogen gas. Now those cancel out, and we simply do the math, and we get 15.7 liters of hydrogen gas at STP. Okay. Okay, I want to do one more to wrap this up. This time I want to go from grams from one element and then go over 2 grams to something else. So let's do this equation right here. So we're going to do 4Fe plus 3O2 yields 2Fe2O3. Okay, and our problem states if we had 1.03 grams of iron rust, how many grams of Fe2O3 form? Okay, now you can always go back to your map if you would like, but we are going to just start here at grams, which is up at the molar mass level. So we need to get 1.03 grams are given of iron. I'm going to need a pretty long one here, so let's keep on going. And the first thing, that's our given, but the first thing I want to do is get the grams of iron to cancel out. So to do that, I need grams per mole of iron. I need my periodic table. So let's go and look at that, and we have 55.6 0.85 grams of iron for every mole of iron. Okay, now they're going to cancel, which is good. Okay, now I need to, I'm going from here and I'm ending here. I want to find out how much mass, how much of this forms. So to do that, I need to go back to my balanced equation and find out the mole to mole ratio. Okay, so I want my moles of iron to cancel out, and I'm going to go and see how much reacted. 4. So 4 moles of iron reacted in 2 moles of Fe2O3 reacted. So now those are gone. Okay, and to finish this up, it didn't ask us to stop at moles, it asked us to stop at grams. So we have to first calculate the molar mass of this entire compound, and if you recall, you have to go find out how much 2 Fe's are worth and 3 O's are worth, add those up, and you should come up with 159.7 grams of Fe2O3 for every mole that reacts of Fe2O3. Okay, after you do the math, you should end up with 1.47 grams of Fe2O3. Okay, so again, these are going to take a little bit of practice. Right now, I'd like you to go and work on the 2 worksheets that are found under the modules. And if you need to, head back to this mole map, because that'll help you as you're going along. Okay, what I did before was I went here from the grams of the iron, and then I moved over to the moles by using the molar mass. Okay, and I found out how many that was. And then once I found out the amount of moles, I used my mole to mole ratio, which is the balanced chemical reaction right here that I need. And that was able to get me to go over here to get the moles of chemical 2. After I applied that molar mass, I was able to find the mass of the iron 2 oxide, or actually it's the iron 3 oxide, Fe2O3. Okay, so I hope that helped. Just work through a few of these, and if you have any questions, just let me know.